Hello everybody, welcome back. Let's talk about the ideal gas law and how real and ideal gases differ from one another. Start, what exactly is the ideal gas law? So the ideal gas law is PV equals nRT, and it's actually derived from the two laws that you learned last week, which is Avogadro's law and combined gas law. And this is how that derivation actually works. So when you combine these two laws together, what you have is something that looks like this. And what happens is, just like how the other laws from last week was derived, these kind of variables, when they combine together like so PV over T and N, it actually equals a constant. And this constant has a name, and we call it R. So this constant R, after you rearrange this equation, you should see that it actually becomes this. So that's how they derived this. We call it an ideal gas law. We use it at any temperature and pressure. So here are the terms of this formula. You have P for pressure, V for volume, and it's very important that it has to be in liters. So if the question gives you a value in milliliter, you have to convert it into liter in order to use this equation. N is your number of moles. T is temperature, it has to be in Kelvin. R is what we call a universal gas constant. And this constant is actually different depending on what units of pressure and volume you use. So later on there will be a chart showing you exactly what sort of R value you should be using depending on what units of pressure and volume you use. So there's a different value when your pressure is in ATM, and there's a different value of R when your pressure is in torr or in millimeter mercury. So just keep an eye out and be sure to use the correct value of R when you do your calculations. Let's next talk about how you would calculate this value of R. And how you're going to go about that is that you're going to take advantage of what you already know about STP, which is standard temperature and pressure. So recall what is the standard temperature and answer the question now. Hopefully you said the standard temperature is 25 degrees Celsius. And then what about the standard pressure? Hopefully you said the standard pressure is 1 atm. So knowing that at STP you have 1 mole of gas has a volume of 22.4 liter, you want to rearrange the equation of PV equal nRT to solve for R, which will give you R equals to PV over NT. When you plug in what you have, so pressure is 1 atm, we just said that it's from STP here. 22.4 liter is from what we know is 1 mole of gas, has a volume of 22.4 liter. The number of moles is 1, and the temperature in Kelvin is 273. That's equivalent of 25 degrees Celsius. That should give you this value. So now this R value is the one that you're going to use when your question gives you the pressure in atm and the volume in liter. Now what happens if we do the same but using a different unit of pressure? Here I'm going to do the same thing, and instead of atm I am going to plug in the number of kilopascal, and that will give me a different R value. And notice the change in units here. So here you have atm, you have kilopascal down here. So always make sure that you are using the correct value of R with units to match the units which you are using to solve the problem. Here is a little table for you as a reference for all the R values according to whichever units of volume and temperature and pressure you're using. Also, as a side note, if you are doing your notes digitally, meaning you're typing in your Google Doc, make sure that when you type in your unit for the R constant, you are typing just like how it looks right here on the screen. So it's very much of a hassle for you to do something like J over K times mole, like that. So you don't have to do that, but it is required that you should do it to make it look like this. So the little dot in between here, it's not necessary, so you don't have to type it in. Just make sure there's a space between each of these units in order to make it clear that that's the unit of R. So since K is in the denominator and moles in the denominator, you can do the exponent of -1 in your note. All right, let's talk about how you would actually use PV equal nRT in a problem. So here I have an example problem giving me a sample of hydrogen gas has a volume of that much. So I'm going to underline that and says that's my V. At a temperature of 0 degrees Celsius, so that is my T, and a pressure of 1.5 atm, so that's my P. Calculate how many moles of hydrogen gas are present in this sample. So they are asking for mole, so that's my missing variable. Now you know that you have to use PV equal nRT because unlike the problems from the last set of videos and notes, this one, the condition didn't change, meaning there's no new pressure, there's no new volume, no new temperature, or new moles. So everything stays the same. They're just asking for, like, at these particular condition, how many moles of hydrogen gas are there? So that's how you know you use PV equal nRT. And that's exactly what we're going to use. Let's write down my given and my missing variable. And here they are. Here's my given, and my missing variable is number of moles. So here I have volume, but it is milliliter. And a couple slides ago, remember that your volume has to be in liter. So I'm going to do that by dividing by 1000 and convert it to liter. So now I have 8.56 liter. And the reason why this volume has to be in liter is because the units of R includes liter. And the reason why I actually chose this R as opposed to the other one that you saw on the table is because my pressure was given in ATM. So the unit in my R value should also be in ATM. Let's go ahead and now rearrange the equation to isolate N or to solve for N. So I'm going to do that by dividing both sides of PV equals nRT by RT. And that should give me this equation. And once I got that equation, it's just a matter of plugging in our given information just like before. And make sure that when you type this unit into your notes, you type it just like how I show in the table in the last slide. So it should be L space ATM space mole -1 or to the exponent of -1, and then space K to the exponent of -1. And then multiply by the temperature in Kelvin, like how we convert it right here. That gives me 0.57 mole of H2 gas. So that's how you go about solving an ideal gas problem. It's just a matter of we've been doing the same thing. Now you just have an extra step of make sure that your R value is the correct R value. The one that you choose is the correct one. Alrighty, let's take a look at how you can use the ideal gas law to solve a different type of problem. So here's my question. The question is, what volume is occupied by this much moles of carbon dioxide gas at 25 degrees Celsius and 371 millimeter mercury? So first of all, I'm always going to identify what's given to me. So here I have N, and then I have temperature, and then I have pressure. Now, of course, make sure that your temperature is in Kelvin, and we're going to do that right now. So let's go ahead and choose that this is my ideal gas law. And I know I'm using this one because there's no change of condition, so there should be no P1, P2, or T1, T2. So none of the 5 equations you learned last week apply here. So it has to be PV equals nRT. Here's my P. My V is what I'm looking for, so it's because it's asking for what volume is occupied. And then N is that. And here is the R value that I chose. And the reason why I chose this R value is because what was given to me in the problem is in millimeter mercury. And we know that millimeter mercury is equal to torr, so it's a 1-to-1 ratio. So this R value would be the only one that would work for us in this case. And then here's T in Kelvin. And now you want to rearrange the equation to solve for V, and you're going to do that by dividing both sides of this equation by P. That should give you this. And then it's a matter of plug and chug. and you should get 12.5 liter of CO2 gas. All right, let's talk about how you can use the ideal gas to calculate density of a gas. And the ideal gas, you can use it to find the density of a gas when the condition is non-standard temperature and pressure. So at any condition that's not at 25 degrees Celsius or 1 atm, you can use the ideal gas law to find the density of this gas. So the density formula is mass per volume, and mass has to be in gram, volume has to be in liter, giving you the density formula is gram per liter. Let's tackle a problem on how you can determine the density of a gas using the ideal gas law. So here I have the questions that says, determine the density of ammonia gas at this particular pressure and temperature, assuming that the ammonia is ideal. Now, what you want to do is, you want to, first of all, step number 1 is to determine the molar mass of ammonia gas. So what is the molar mass of ammonia? Hopefully you said it is 17.04 gram per mole. That's just straight out of the periodic table. Step number 2 is that you want to assume that there's exactly 1 mole of ammonia, and then calculate the volume that this 1 mole occupies using our ideal gas law. And I know that my ideal gas law is PV equals nRT. So like always, you want to rearrange this equation to give you a V on one side and everything on the rest. So it should look like so. V is equal to nRT over P. Now it is your turn to identify which of the number for each of these variable. All right, hopefully you said that N is 1 mole, and that is because we exactly said that there's 1 mole of ammonia right there. We assumed that. And you should have chosen this R value because ATM is the pressure that was given to you in the beginning. And then 293 Kelvin is from this 20 degrees Celsius. And this pressure is just from here. And then you should get this number as your final answer. Okay, then step number 3 is you want to calculate the density now by dividing the mass of 1 mole of ammonia by the volume of step 2. From step number 2. So here's the equation for density, mass over volume. What is the value for mass that I'm going to plug in right here? And what is the value for V when I want to plug in right here? Hopefully you said that mass is just the molar mass that we calculated. The molar mass is gram per mole, and we do have just 1 mole. So it goes right there in M, and V is just what we got from our previous step. When you do your calculation or your division, you should get this number as your final answer. All right, that wraps up this video. Thank you for your attention, and I will see you in class.